normal mechanisms, and Samos was one of the extensional ones. And here we have many in the region. We have many active faults which have been already mapped and already missing some of those faults also. So there's a lot of discussion on those also. But it's a very complex area, as you see. This is the fault map is compiled from the active fault map of Emre et al. And here I want to show you some of these field photos of these that we took during our investigations. Here, one of the photos is showing this strike slip motion on the Tuzla fault. Next to that fault, there is near the Kuşadası, we have a normal faulting. You can see the slip direction where the motion is going on, shown by arrows on the scarp. So basically, you can see both of these type of faults are active. Here, actually, Professor Zeynep is getting acquainted with detecting active faults in the field. And we have another picture on near the famous, I think this is a hotel, Adakale hotel, which is next to the scarp of the fault. So if we look at the earthquake itself, the mechanism is almost pure extensional mechanism. And if we, for the people who are not familiar with these type of plots, basically if we take a cross section, we would be seeing the section of the fault plane, which would be slightly shallow dipping, so gently dipping, and the nodal plane is also shown with dashed lines. So basically, we are preferring a north dipping fault plane at this point. Here, if we look at the focal mechanism solutions, CMT solutions, we see that the extension is pretty clear. The focal mechanism solutions are robust and showing similar characteristics. But one of the important things is they are giving significantly variable dip amounts. That might be an important issue in the further analysis. Plus, the location of the earthquake, if it's a gently dipping event, is basically a bit in the deeper side. So we use the CMT solution, which uses the most data, global CMT solution, for our fault parameter for the strike and dip. And we use the Kandilli's hypocenter for the initiation of the fault. Another thing to also state is basically the share database that is compiled in 2013 was also showing this fault that we think is activated during the earthquake, which was a pretty good match. If you look at the GPS data, besides the seismic data, also the extensional motion, this horizontal motion apart from each other towards north and south, is indicating this extension clearly. Also, at the Samos Island, there's significant amount of vertical motion, which is reaching up to 10 centimeters, and you can see the implications of that in the figure. So once we look at with the satellite images, we can identify the vertical motions, and we also see a peculiar part here, which is subsiding, and this might be a secondary faulting, or maybe the fault is reaching to the land. And this is the region where we see this subsidence reaching up to 10 centimeters is where there is a fault, known fault is located, which I'm showing the photograph. The uplift that we are seeing mainly in the western part of the island is basically due to the release of the load. You are having a footwall uplift that was expected from this type of normal faulting. So INSAR and GPS modeling together, there are many different groups are working on this simultaneously, and they are also finding the strike slightly bit towards northwesterly. So you can see the dimensions are pretty similar, and it's pretty good match with the seismic interpretations also. So preliminary teleseismic rupture models, USGS model here, and still I think this is the model that is posted on their website, is using a hypocenter, significantly deep hypocenter, which is 21, and seems to basically sensitive to the rupture mechanism is sensitive to that hypocenter, and it seems like the rupture is not cutting to the surface and passing through the Samos Island, so it's not a good finite solution. Whereas the solutions, for example, Okuwaki had a solution. This time, his solution was the magnitude was 7.1, and it was showing as if it reaches the displacements were reaching to the surface at the Turkey mainland. But in our field observations, we haven't detected any kind of ground displacement, surface displacement. So we think this type of large area is not also fitting to the picture. Serkan Irmak in the below picture, you have a finite fault. You can see it's around 30 to 40 kilometer long, and they were using similarly the CMT's strike and dip, and this one is also in a similar one. This one is also using S waves, so it's better result. As you see, we have a good initial result for the finite fault. So based on those, we kind of simplify the fault area, rupture area, and here in the table you are seeing the preliminary determination of our rupture parameters that we used for our reconnaissance work. It was 35 kilometers selected for the length, width is selected 15 kilometers, and this was creating a rupture with a depth range of 0 to 9 kilometers with an average slip 1.5 meters, and we use the CMT. So this is actually a simplified version. We should be careful about this. We know this earthquake is, the rupture plane is significantly a complex one. It's changing in strike, even in dip, through its rupture process. So these rupture models are still ongoing research. And you can see the aftershocks are pretty well fitting with the rupture area that we are defining. Basically, the lack of aftershocks in the middle is where the most slip release is occurring from the finite solution. There was two peculiar clusters. One was in the west that seemed to be correlating with a strike slip fault, which we identified with dashed line here. And there's another cluster in the south east of the island where we see its different faults are getting activated. So if we look at those, the AFAT solutions for that cluster in the west seems to show clearly the strike slip component. So slightly a different fault is activated in that western edge. And if we look at the distribution of aftershocks through time, we also see that along the first day or so, or the second day, it was all located around the rupture area. But then there was a migration towards southeast, where we started to see some of these activated clusters are getting activated. And actually, this is indicating a delayed triggering, 2 days delayed triggering on this small faults located in the eastern part of the island near Dilek Peninsula. Okay, so since there was the most damage was identified nearby Izmir, maybe a little bit more focus on the geology would be appropriate. So here is a geological map. Mainly the units in the region is Bornova Filish and also volcanics, but mainly the damage area where most ground motions are recorded by AFAT stations are near the Bornova plain. And if you look at the Bornova plain, basically Holocene sea level is significantly matching with the heavily damaged area. We are I'm plotting this in a kind of a Google Earth image. You can see the bounding faults of the Bornova plain in both sides from north and south very clearly, and you can see in the photograph also the continuation where these faults are located, which details of this is given in the reporting. And previously in 2017, there was a publication that I see that they modeled the gravity data and find this density significantly low, thick, low density material to be present. So we know the basin field is pretty thick, and the VS velocities are significantly low. So this would be a candidate for likely site amplifications that will be not other speakers will talk about it in more detail. So let's see how severe the risk by looking into the seismic history of the Izmir. And if you look at this, the stars are representing the earthquakes that were damaging, historical earthquakes. And actually there are several earthquakes that created in the Izmir Bay tsunami. So you can see that there are many active faults. This is Izmir fault bounding the bay from the south, and this is Karşıyaka fault bounding the bay from the north. And there are along the bay also there are active faulting, which is causing tsunami and very frequent damaging earthquakes. So we have a very imminent threat in that sense respect to Izmir. So, but I will be finalizing my words. Is basically in order to identify what is the risk in a region, basically we should know our conditions. So one of the things is we should verify our active fault maps. Probably there are missing faults still that we need to do some work to identify it. And another thing is, even though we do seismic hazard assessments, one of the big issue is sometimes we should learn, we should put the time constraint also to these assessments in order for the places where the threat is imminent. So we should find out if this fault is in a stressed time or already the stress is released on that fault is going to be very crucial. Also, it would require some trenching and geodetic work to be conducted with the combination of seismic analysis. So multidisciplinary approaches are going to be very valuable in these regions where the site characteristics are also very poor. So thank you for your attention. This was a fox that we identified in the Dilek National Park during the field. So I think we will have the questions at the end, so I will finish it at this point.
Thank you, Dr. Özacar. Our next presenter will be Dr. Ayşegül Askan Gündoğan. She will give a speech about strong ground motion distributions and intensities.
Hello, everyone. Thank you for being with us here today. Gizem, can you see my slides?
Yes, hocam.
Okay. All right. Okay. So let me put it into the presentation mode. So I will try to stick to my 10 minutes and I am just checking my watch here. So today I will give you a very brief introduction on the observation on the recorded strong ground motions and intensity distributions. This is a joint work with our colleagues and young students. So when the 1906 big San Francisco earthquake happened, the three main issues about the earthquakes were listed as the physical earthquake event itself, the associated ground motions, and the effect on the structure. So this is a sketch that I use in the classes also. I would like to show it to our students who are here. Significance of ground motions is actually shown in this figure, and they are the signature of the earthquakes, and they help us to understand what's happening from the source throughout the path, having the side effects, and it is the combination, it's the bridge between the earthquake effects and the structural effects. That's why I find ground motions particularly important in assessing the earthquakes. So these are the major tectonic structures of Turkey. I'm not going to go into source. Arda Hoca has already done it, but most of the earthquakes are going to that we hear are happening on the east, North Anatolian faults, or in the Aegean area where the Samos event has actually occurred. So our recent seismic hazard map of Turkey gives us a similar hazard areas. I'm not going to say zones because the zones are over, but it gives us similar high hazard regions. What you see here is the 475-year return period peak ground acceleration. So let's look at the 30th October 2002 event. These strong ground motions, well, we had about 33 strong ground motions within 100 kilometer epicentral distance, while we have 83 a total within the 200 kilometer distance. The data is available both filtered and raw at the AFAD's new website right here. We do not have too many near field records if we consider the near field definition to be equal to the fault size actually, but we have some records to take a look at closely. I will show you today the records in Kuşadası around here, and a few in the basin, and this record over here with the highest ground motion values. Well, we do not have really high ground motion values when we look at the peak ground accelerations, but we still have some signatures of the event. The highest being in Kuşadası, about 0.18 G, while we have lower values within the Izmir basin here. But I don't want you to suffocate in numbers, but what I will focus on is the corresponding actually ground motion effects, let's say the signature. And I actually made a map here with the time histories for your amplitude spectra and the response spectra for these 6 records that I selected. And you will see that we have actually varying site conditions over here. I'm going to go really quickly over these ones. We have a VS30 of 500 around here. We have short period amplification as we expect. And actually in Kuşadası, we have, I'm showing you comparisons with the last earthquake code with the 2007 code and the 1975 code, because in Izmir, especially in the Bayraklı region, the buildings, we actually considered them being built according to the 1975 codes. Around this area, coming back to Kuşadası, we see that there are some spikes over the 1975 code, but we don't have much or many actually records of damage here that are significant. I would like to focus on the Bayraklı region, on these 2 stations, which you could further actually analyze in the report that we published. This station is on a VS30 of 800 meters per second, whereas the other one, 3513, is on a softer soil, about 200 meters per second. Well, what I see immediately is the station on the softer soil has definitely some long period amplifications. You could see the plateau here where I'm showing you, and it is really close to the codes actually. It's closer to the current code than the 2007 code in the long period region, but it is below the code anyways. And in 3514, even though we don't see such an amplification in the term of peaks and in terms of some peaks, I still see some elongation, and this is really there in the significant durations as well as areas intensities and Hausner intensities. Hausner intensities are related to the pseudospectral velocities, which I think are important when we actually talk about the structural damage. So in short, I think there is not only a side amplification effect, but as Roger is going to talk about, there is also a major basin effect here, which made predominant long period, longer duration, typical basin response. And a very quick look at the HVSR. HVSR is the horizontal to vertical Fourier amplitude spectra. This is non-filtered, non-smoothed, everything is raw. What I see here is on the softer soil conditions within the basin, we see some lower frequency peaks, that's okay, with the side amplification and the basin effects. And we have less pronounced peaks for the rock station 3514. And again, I cannot say this is a classical HVSR of a classical rock station. And I know the soil mechanics lab is going to focus on this in detail. So let's talk about the intensity distribution. I want our actually young colleagues and students to hear about it in detail. Intensity was a major measure of ground motions maybe half a century ago. But then after the installation of the strong ground motion network, it was kind of abandoned. Now we are back to intensity. Why? Because before everything else can be assessed, we have access to this MMI, MSK, JMA scales, and we have actually maps that help us to reach to the mesoseismal area. We have sources to find out where is shaking the most. And with these tools, with MMI, ground motion intensity correlations, we can assess the past earthquakes. This is the 1999 Kocaeli event on the field. This is the MMI map on the field. These are our models. And we can also assess pre-instrumental era earthquakes. This is the 1939 Erzincan earthquake, which is observations versus the models. So let's look at the intensity distributions of the Samos event. We see that this is the AFAT-RED system output, the immediate output from the AFAT-RED system. It gives an MMI of value of maximum maybe 5 and 6 around Izmir area. This is the values we obtain from our local correlations between MMI and PGV. And when you plot in PGV of the actual stations, and when you have a contour map, this is MMI 7, where actually structural damage starts in the Bayraklı region. So I think this is a valuable piece of information. Let me conclude this very short talk. We have a combination of basin and side amplification effects that is reflected in the spectral values and significant durations. We are still below the code, but we have to make detailed assessments on the long period amplification range of the spectral accelerations with the current code. We have to do further talks about it, further reports about it. MMI distributions based on PGV indicate Bayraklı as the maximum MMI area of 7. We will model these ground motions in detail through simulations if we can find detailed velocity models. I should comment that we had a big interest in this event when compared to the other earthquakes in the other regions in Turkey. So that's something to be, I think, highlighted. Well, in theory, we have the recent fault maps, hazard maps, building codes. We are very good on paper. We have good engineering schools. We have good earthquake engineering classes and programs, but something is still very wrong on the field. And I will stop with the resilience concept that our students should hear and learn about. It's not a fancy term anymore. We have to learn how to be resilient to multiple hazards, including, look at us, diseases, earthquakes, and fires, and landslides, and floods. So we have to learn to be a resilient society. I'm showing you figures from San Francisco and Japan earthquakes. I would like to thank to all of our team members. These are the reports available online. And if you have any questions, I will be willing to answer them in the end or through email. Thank you very much.
Thank you, Dr. Aslan. Our next presenter will be Dr. Zeynep Gülerci. Her speech will be about ground motion prediction models.
Gizem, thank you very much. I'm sharing my screen right now. All right. Can you see it now?
Yes, hocam.
Okay, thank you very much. So my focus today will be on the predictive performance of ground motion models from the recorded strong motions in this Samos or Aegean sea earthquake. Here is the list of authors that we work on this together, and I also would like to acknowledge the other members of our team. We go to the field together and collect all of this information together. So I can see that in the audience, we have a complex system. We have distinguished researchers who know everything about the ground motions, but the target audience was the students. So my presentation will be clear and quite basic in terms of ground motion prediction models to be able to reach all of the students that's right now here. All right, so what is a ground motion model? A ground motion model, or a GMPE, is a tool actually that converts your earthquake scenario in terms of the expected magnitude, the distance to your fault or to your source, and other parameters to the ground shaking levels, which in our case, the accelerations, because force is equal to mass time accelerations, and if we know the acceleration, we can calculate the horizontal forces that we are going to use in earthquake resistant design. So a ground motion model is something that is used to convert the information comes from the earth scientists to the information that the earthquake engineering can be used. So these ground motions, or the estimated design ground motions, are used in structural and geotechnical analysis, dynamic analysis. They are used in hazard maps, and they are used in design codes. So these ground motion models, on the other hand, only as good as the empirical data sets And in terms of empirical data sets, we can divide them into two broad groups. The first one is the global model that combines the data from the same tectonic regime. In our case, for Turkey, the tectonic regime is the shallow crustal earthquakes in active tectonic regions. If you combine the data from different countries or regions together, you will end up with a larger data set, which is statistically more stable. The other option is to use regional or local models. The local models use the data from a particular region. For our case, this is the Turkish Strong Motion database. In that case, we will have a smaller data set, but the data set will be more representative for regional characteristics. We can use the ground motion models from both options, but it is quite controversial and a matter of discussion which one to choose, which one to use. And interestingly, choosing the ground motion from one set or the other set changes the design ground motions by a factor of 2. So it's an important decision. So my final word here is that each well-recorded earthquake is an opportunity to test our available ground motion models and to test our choices. So the question is this earthquake well recorded? The answer is yes and no. So in the screen you are seeing the strong motion stations of Turkey with black rectangles, and you see the approximate rough rupture plane with the yellow rectangle, and the epicenter is the red dot. So we can say that the earthquake is well recorded because there are 83 stations of Afat that have rupture distances smaller than 200 kilometers. This is not a bad number. The answer is kind of no, because out of these 83 stations, 17 stations were deployed quite recently, I mean less than 3-4 years ago. Therefore, their site characterization is not complete yet. So we don't know the site characterization values, VS30, or anything else about these sites. So these stations will not be able to use in our testing procedure. The other important issue is we don't have any recording stations closer than 30 kilometers to the rupture plane. As you can see on the screen, our nearby station, the nearest station, is approximately 32 kilometers away from the rupture plane. On the other hand, the Greek seismic networks are also recording this earthquake, and the Greek seismic networks have 2 stations on the Samos Island, so a joint database would be better to be able to test the predictive performance of the ground motion models. On the other hand, unfortunately, because of the dipping plane, dipping direction of this earthquake, the closest station coming from the Greek side is also only 12 kilometers away from the source. So in the bottom line, this earthquake is a suitable candidate to test the available ground motion models. Now I'm going to show you how this test is performed. The typical way that we perform this test is we calculate the residual, and it is very simple. The actual data recorded at the station and minus the model prediction gives you the residual. The residual can be positive or negative. The positive residual means that the data is bigger than the prediction, so the model is under predicting the data. A negative residual means that the data is higher, the negative residual means that the data is smaller than the prediction, so the models over predict that data. In one station we may have a positive, in other station we may have a negative residual. The important thing is what is the average residual for this earthquake. So you can see in the screen the average residual for this earthquake based on the global models and the local models. For the global models, I'm using the MGA West 2 models, which were published on 2014. For the regional models, I'm using the Turkey adjusted models, which was published in 2016. As you can see that the average residuals are generally negative, which means that the ground motion models overpredict this earthquake, especially at shorter periods, up to 0.4 or 0.5 seconds. But the picture is different if you go to longer spectral periods, especially after 0.75 seconds, up to 2 seconds, the average residuals are positive, indicating that the ground motions, recorded ground motions, are significantly higher than the model predictions in these particular periods. This is valid for the global models, but if you look at the regional models, we don't see that difference that much. In particular, the average residual is negative, That means for almost all cases, we have over-prediction for this earthquake. Am I taking too much time? Let me move on. The other way that we test the predictive performance of the ground motion models is we look at the distance attenuation. And this is an example, 2 example plots of distance attenuation. The first example is a good example. Here in this example, the black line is the median estimation of the model, and the broken lines are the plus minus 1 sigma of that particular model. And this is a good example because almost all the recorded motions lie within median plus minus 1 sigma, except for a few far-field stations. Okay? So if you look at all candidate or all tested models, the short period distance attenuation is generally sufficient, and the best fit is achieved by Abramson et al. 2014, Campbell and Bozorgnia, and Chu and Young's 2014 models, or the NGA West 2 models, and one of the Turkey adjusted models has also a good fit with the short period attenuation. Another very good example is on the right-hand side. We can see here, this says PJ, but this is a mistake. This needs to be spectral acceleration at 1 second. I'm sorry about that. So if you look at this not very good example, there is typical, very quite clear under prediction of the stations at 60 to 70 kilometers away from the source. And these are Izmir stations, actually. And we also see some over prediction for some far-field station. This picture is generally valid for long periods for almost all ground motion models, and the best fit is achieved again with Campbell and Bozorgnia model and 2 of the Turkey adjusted models, as you can see on the screen. So the question here is really the Izmir recordings are so different in terms of ground motion prediction? Here is my last slide. I collected the recording stations within the Izmir metropolitan area, as you can see on the screen, and I'm using 4 spectral periods here: the peak ground acceleration, 0.2 second, 1 second, and 2 second predictions. And this is the VS30 scaling of the candidate models. What does it mean? This is peak ground acceleration. As the VS30 increases, as the site becomes stiffer, the peak ground acceleration decreases according to the model. And the dots are the recorded data points. And as you can see, there is a scatter, of course, among the models, but the points are in a good agreement, we can say, with the models for peak ground accelerations. Please keep in mind that these are Izmir dots, so Izmir recordings. If you go to 0.2 seconds, again, we can see that the points are within the expected scatter. But if we go to 1 second spectral accelerations, the picture is completely different. Okay, the recorded motions, especially on 1 second spectral accelerations, are far, far more higher than the model predictions, no matter which model is used, the Turkey adjusted or the global models. If we go to just 2 seconds, the picture is completely different. Okay, we can see that there is again an almost good fit with the model predictions and recorded data. So this is something that is special to 0.8 up to 1.5 second spectral accelerations. Here is my concluding remarks. I hope I'm not taking too much time. This earthquake provides a good opportunity to test the available ground motion prediction models, especially for some of you might know that many of the global data sets are rich in strike slip events, they are rich in reverse events, but they are not very rich in normal earthquakes. This is a well-recorded normal earthquake, so it's a good opportunity for us to test the ground motion prediction models. Good news is the distance attenuation of the tested ground motion models is consistent with the recorded data, especially for distances less than 100 or 120 kilometers. After that point, the differences in the inelastic attenuation Q changes a little bit. The performance is not that good, but this interpretation is right now a little bit raw because I'm going to add the stations from Greece, seismic networks, and then these interpretations will be much more valuable because when we will have these near fault recordings from the Greece seismic network. The average residuals for that particular event is within the expected scatter. Even if that they are quite negative, but they are not very large in terms of negative residuals. For most of the ground motion models, they are lying within the expected scatter, except for a certain period range, and that period range is 0.8 up to 1.5 spectral second. And what's going on in this particular range is the contribution of the recordings from the Izmir metropolitan area to this misfit at that particular period is very significant. And this is because of the site amplifications observed in Izmir, which will be explained very well by Önder Hoca in the next presentation. But this is a noteworthy thing to remember. And finally, I'm going to say that we are almost done on a manuscript that presents a lot of more distance attenuations, a lot more detailed analysis of the prediction performance of the current ground motion models. So please stay tuned. If you want further information, we have the reports that are published on the ZIMAM website. Thank you very much.
Thank you, Dr. Gülerce, for your very detailed speech. With Dr. Gülerce's speech, I think our session about strong ground motion intensity and ground motion prediction models is ended. Ahmet Hocam, if you want, we can start the Q&A session.
Gizem, I think it is better we postpone the discussions to the end. So let's proceed with Professor Yalçıner, please.
Yes, Gizem,
Okay,
that's
hocam.
right.
I will make Dr. Yalçıner presenter. Hocam, you can start your speech.
Thank you, Gizem, and welcome everybody. I'm now sharing my screen and start presentation. I hope you see the screen
Yes, hocam.
and clearly hear my voice. Thank you again, and I'm going to present the post-tsunami field survey results that has been collected just after the event by the and Yıldız Teknik University, Kocaeli University, and Dokuzey University, and Izmir, Istanbul Metropolitan Municipality. Also, in the beginning, I have to thank TÜBİTAK and Yüksel Proje for their monetary support to this survey. And everything has been explained previously about introductory slide for tsunami information, because all tsunamis in general is generated by the earthquakes and seismic activities. As you know, the epicenter is shown on the map, and the tsunami is generated, and the fault lies east-west direction approximately, and in general, tsunami's directivity or energy, so tsunami propagated north and south, and at northwards, inside the yellow square rectangle, there was major impact of tsunami, and we have made surveys in the region. And the main information about the tsunami field surveys, first of all, we went to the north, the central, and southern part of the region, and those are shown in the map, and there were different action and the impact of the tsunami in the region. Why we went the area very quickly? Because tsunami leave various marks in the areas where they are effective, and though the traces left by tsunamis may disappear in a short time. Very important to understand the behavior of the tsunami. at the coastal areas, and we have to measure the run-up, flow depth, inundation distance, and arrival time and damage levels at site, and eyewitness reports, interviews, and interpreting video records are very important supporting methods to identify the other unknown parameters of tsunamis. So we did those, and there is a UNESCO post-tsunami field guide published in 2014. I was the author of that important document. Post-tsunami field survey has been also applied in this study to make it a location that was hit by tsunami, where Theos Marina and nearby fishery port had major effect. Is the name consisted of Su and Nami wave. All tsunamis, even if it is small size, they are effective on the at harbor. So Japanese called the name tsunami to this wave. And Swagic Theos Marina is located on the north port of ancient Theos city. And inside the Swagic Bay, and Swagic is a low elevation, shallow depth, low elevation land, shallow depth bay. It was very, very active, and almost 15 minutes after the earthquake, the sea and the boat sank down inside the marina. Some of them stuck at the muddy ground, and after that, when the wave advanced, it got very strong. One of the major effects of the dragging of 3 pontoons with more than 300 boats inside the marina was the small stream bed going to the marina collected all the inundated tsunami wave water and discharged them into the marina. It caused very, very strong. And these are the damage and the tsunami traces at the railings of the marina border. The tsunami traces inside the restaurants and the marketplace shops. Another important location was Akarca, 8 kilometers south of Sığacık. It is there was a small fishery harbor in the region with a not so good engineered structures and floating structures, and all of them dragged by the tsunami. And these are the damages at the fishery harbor. The Seferihisar diving center, Akarca, was the most hit location, and the water level was 1.1 meters splash height near the house in the location, and the other photographs show the tsunami deposits and also inland dragging boats. Theos ancient city is another interesting location that the inundation distance was measured as 552 meters from the southern port of Theos ancient city. Theos ancient city had two ports that was in location of the Theos Marina today, and second one is untouched archaeological site. The photograph is shown here, but it is also located at the end of a stream bed, and tsunami likes the stream beds, rivers very much, and penetrates into the inland along the stream beds. We have seen the same behavior of tsunami in the event, in this event. And this is the findings from the north part at Alaçatı. Alaçatı Azmak is an interesting stream bed, and it goes more than 3 kilometers inland, and starting from in the north. A boat was dragged 1,162 meters from the shore, and the maximum penetration of tsunami along this Azmak River was about 2.5 kilometers. And it was interesting that one of the dolphin was also dragged by tsunami, and it was found 1 kilometer inland from the sea, which was interesting because the dolphin can also swim at the extreme conditions, but this tsunami was stronger than the dolphin in the region. Port Alaçatı is another marina. There was 72 meters inundation distance in the almost 1 meter water level increase at the marina region. Zeytineli is south of Alaçatı, and this is one of the unengineered coastal structures very clearly damaged by tsunami. And this tsunami was not very strong tsunami, but it also damaged the coastal structures and the marine vessels. Zeytineli, another location, the tsunami dragged 1 ton weight blocks in along the coastline and penetrated inside the inland side along the lowland areas and the stream beds. Demircili and Altınköy are other similar examples of the tsunami damages. According to our observations, we can make a summary here that, first of all, Sığacık and Akarca regions are the most hit areas of the tsunami. And the highest run-up is measured about 2.18 meters at Teos Lodge Cafe, and in Sığacık 413 meter inundation was observed. In Akarca 3.80 meters run-up observed with a 91 meters inland location. Distance was measured 285 meters. Maximum penetration of this tsunami observed in Alaçatı Azmak 2,487 meters. Ancient Teos in southern harbor. Now also there was 552 meters inundation. This inundation followed the old harbor area of ancient. And interpretation of our results in general, the modeling is very good tool to show the results. There were different fault mechanism interpretations, and also Arda Hoca and Zeynep Hoca is in our collaborator to understand the fine analysis of the source mechanism of this tsunami. Mainly the fault behavior caused the subsidence of water level in about elliptical direction with a 1.8 meter displacement at the hypocenter. This is one of the assumption of the initial parameters of tsunami generation, and we make the tsunami survey, the tsunami numerical model. Example, of the tsunami behavior one last chance to another media player for the last presentation. I think you see the wave propagation. This is the near analysis. Water resilience is the first wave. The subset of water and red containers are the advancing of tsunami wind and water level. And red are also inundation also. Performance, I can start question and I can explain you that what I have explained. One is the Sığacık Marina, another one is the Sığacık area, the most strict areas. The red color becomes darker. Another one, Theos, ancient city, Southern Harbor. Southern Harbor was affected significantly by this, and I come to the comparison of the water level they are satisfactory. Finally, I would like to thank everybody for the kind attention, and also Earthquake Engineering Research Center of METU for this very important event and identification of efforts and other activities by the members. All of them are very much acknowledged by ourselves. Thank you very much.
Thank you, Dr. Yalçıner. Our next speaker is Dr. Kemal Önder Çetin. His speak will be about site effects and geotechnical reconnaissance findings. Hocam, can you hear me? Oh.
Which was established by a big group of contributors. So we have a lot of contributors for these studies. Some of them are METU faculty and graduate students. We have a lot of local faculty members, as well as Professor Akgün, Professor was kind to join and Professor Özacar, who helped us with the basically the geological aspects and source characterization aspects. Also in the team as one of the members, we have Professor Yilmaz, who contributed for the performance of earthfill and rockfill dams and contributed for the reconnaissance findings regarding that aspect. Before we jump into the discussion of geotechnical reconnaissance findings, I would like to bombard you with a lot of pictures and a lot of aspects that we have documented when we're in the field. Please note that the major point of reconnaissance studies is to basically document perishable data. So on the way, we have documented some data related to tsunamis, some structural performance data as well, which we'll briefly present, show it, but the in-depth discussions are covered by true experts of the problem. So please don't forget that. And my two colleagues, Ms. Gizem Can and Makbule Ilgaç, who will be very soon, I'll be very happy to call them as Dr. Can and Dr. Ilgaç. They have a couple of months left to complete their PhDs, will join me to present some of those findings. And maybe no further ado, I would like to first ask Ms. Can to present reconnaissance findings about liquefaction.
Thank you, Professor Çetin. Good afternoon, my dear professors and attendees. As Professor Çetin mentioned, but let me repeat, my name is Gizem Can. I am a PhD candidate in our civil engineering department. As Professor Çetin mentioned, we have visited the potential liquefiable alluvial basins. Hocam, maybe you can show the map, as shown in our map here on the right. For that purpose, we have used USGS liquefaction susceptibility map to get an initial understanding of the region. We have visited all the coastal regions, starting from Urla till Kuşadası Davutlar. However, we did not find any surface manifestations, especially in the south of, especially in the Çeşme and also in the south of Seferihisar regions. But even though we couldn't find any surface manifestations, we have still documented them to make our work complete. And also, please keep in mind that non-failure sites are also as important as the failure sites. Therefore, we visited all the coastal regions, all the beaches, even though they are non-liquefiable. We have documented them. We took some pictures from those sites. And yeah.
Thank you, Gizem. Now I'm going to ask Ms. Ilgaç to present one wonderful surface manifestation of soil liquefaction.
Hocam, thank you. My name is Makbule İlgaç. I am research assistant and PhD student at METU, Civil Engineering Department. On the first day of our reconnaissance, Gizem and I were driving along the northern coast of İzmir Peninsula. And we have stopped by a beach in Gülbahçe where we have found this beautiful sand boil. I say beautiful because our research is about liquefaction, so we got pretty excited when we found this surface manifestation of liquefaction. We took photos, we collected samples, and we brought all the samples back to the campus. And thanks to our friend Mutasam, he has performed a series of sieve analysis, and he has later informed us that the samples are exactly falling in the range of potential liquefiable soils. Yeah, we took a lot of pictures, and after we turned back from, Hocam, could you please go back? After we turned back from İzmir, we have some interesting information about the site. One of them is that this liquefied site was the only site in Anatolian part that has liquefied after 2020 Samos-Izmir earthquake. Although we know that there are surface manifestation of liquefaction in Samos Island, that was the only site. And the site is located about 50 kilometers away from the epicenter, and the PGA levels are relatively lower, and they are around 0.05 to 0.1 G. So that might be probably the lowest PGA level that can trigger a surface manifestation of liquefaction. Another thing that we have learned about the site, that there are some hot springs on this region, and that might also contribute to the liquefaction. So that site might not be a very typical case study for liquefaction, But we were pretty excited that this combined effect of hot springs and the earthquake has caused liquefaction. And then hocam, we drove south to Sığacık. Professor Ahmet Yalçıner hocam has discussed the tsunami in quite detail, but we also visited the site and see the trace of flooding, the fishes left behind the flooding, and all the traces. We have seen the toppled boats and documented them.
Thank you, Makbule. Also, Professor Yılmaz, part of the Earthquake Engineering Research Center, a member of it, visited some of the earthfill and rockfill dams. We have also joined some of the reconnaissance activities. Luckily, there are no dams, rockfill dams or earthfill dams that were damaged after the event. All the performance is mostly elastic, except in one reinforced concrete phase rockfill dam that a minor cracking was observed. So we have clearly documented that there was no damage in these earthfill and rockfill dams, and some of which were, relatively speaking, shaken by moderate level of excitations in the range of 0.1 to 0.15 Gs. These are the pictures. Tahtalı Dam, we have 2 accelerometers, which is also part of the database that we have used. Having said that, again, Ms. Can, would you tell us quickly about the foundation performance of the buildings throughout our reconnaissance path?
Of course, hocam, even though it is not our scope of the geotechnical findings part, our structural engineering faculty members will discuss them very detailedly next. But on the way on our road, I hope you can hear me.
There's no signs of settlement and so on. And again, Gizem, are you back?
Hocam, sorry, I lost the connection.
It is okay. This happens. And also, we have documented some of the rock failures as well as good performances of the slopes, both soil slopes and rock slopes. You can see that on the shoulders of the highways. The performance is great. Again, these are the quick pictures. Some bridge performances will be beautifully covered by the rest of the reconnaissance team. Having said that, what I would like to do next is remember now this is an event by Samos Island, and for some reason, about 65 to 75 kilometers away from the source, we have some concentrated damage. So the red dots are basically the locations of heavy to fully collapse building damages that we see or concentrated in basically Bayraklı region. So having said that, you can see some of the vivid pictures. We lost more than hundreds of our lives in this small neighborhood, and definitely that deserves a lot of attention to understand the reasons behind this phenomena, this concentrated damage in Bayraklı region. Here is basically a picture that we took when we were there about the foundation system of one of the collapsed buildings. So honestly, we have not seen any evidence suggesting that this, even relatively speaking, not very seismically resistant two-way foundation system performed really well. So they did well. They're not mat foundations. They don't have pile systems and so on. We took some samples from the foundation. So definitely the reason of the damage cannot be attributed to foundation performance. Then we need to focus on what is the reason behind this concentrated damage, again, in addition to structural detailing issues. I would mostly focus on the geotechnical factors, and you can find more about what we will present in the basically report that we have prepared as part of Reconnaissance Studies. So I'm going to go back and discuss the site conditions and its effects on structural damage on a more detailed manner. So to be able to understand what happened in Izmir Bay, we need to first understand if the reason is because of the source or because of the path effects when the wave is traveling all the way to Izmir Bay. To be able to answer that question, I will compare the Samos Island record. By the way, this is a soft rock site with a shear wave velocity of 380 plus meter per second, so it is not a typical rock site. And the green curve is our ground motion prediction equations. As you can see that for some unknown reason, we have some long period energy concentrated in the range of maybe 0.5 to 1.5 seconds, or maybe slightly less than 1 second in that source region. So this is something we don't expect from such an event. Let's go on the way. Again, another rock site. This is our 35-36 site. Again, let's compare it with ground motion prediction equations. You see that unusual long period energy is still there. Remember, this is a rock site. So we don't expect really like long period energy at rock sites. So now we came to Izmir Bay. Let's look at the motions at Izmir Bay. Again, another rock site. And that long period energy is still there. So this is the first essence of the story, is that this event particularly produced long period energy at the source, which was present at the source. And all the way when it's traveling towards Izmir Bay, that long period energy was still preserved. So that was one conclusion that I will share with you. Okay, let's take a look at the Izmir Bay rock motions. And then let's see if we can really mimic those motions. There, I would like to ask some help from Ms. Can. Gizem, would you please elaborate on the rock records obtained along Izmir Bay?
Yes, hocam. Here, around the Izmir Bay area, we have mainly 5 different rock stations. Their VS30 values are around 70 to 875 meters per second. We will look them detailedly one by one. How is their surface recordings, I mean the rock outcrop motions, along with the response spectra. Here the first station is the 3506, has a VS30 value of 771 meters per second. You can see acceleration, displacement and velocity time histories with the Fourier amplitude spectrums. When we compare the response spectra with the available ground motion prediction models, we selected Abramson and Silva 2014 from NGA-GRAS2 model, as it is very well explained from Dr. Gülerce. They are compatible to each other just for the period range of 0.5 to 0.8. Ground motion prediction models does not capture the response for this station. For the next station, we are going all the way. If you see the map, we moved now to Kaynaklar station in the İzmir net. AFAD's correspondence of this station is a 3517. Again, we did the same exercise. You can see the surface recording of that site with the ground motion prediction estimations. For this record, we have the ground motion prediction models overestimate the period range for the short period ranges. However, for the higher period ranges, they are giving less results. And then the next station is the Bornova. Now we are getting close to the region that we see the side effects mostly. Here again, we gave the response spectra for 5% damping. If you see, the surface recordings are very rich in the higher period ranges for these stations when we come closer to the İzmir Bay area after the 0.7 to 1.5 seconds intervals. And this is the Manavkuyu station. Again, the Fourier amplitude spectrums. We put the Fourier amplitude spectrums to find the fundamental periods of the site actually. And if you see the response spectra with the ground motion prediction estimations, now even the PGA values and also the higher period ranges, the ground motion prediction estimations unfortunately does not capture the behavior for this sites. For the Bayraklı also, we have the same thing, we have the same problem. If you remember, for Bayraklı, the collapsed buildings was the 7 to 8 story buildings. That means the period range is actually 0.7 to 1 second, but the ground motion prediction models unfortunately does not capture for that period ranges. And the VS30 value for this station is 836, which is a typical rock station.
Gizem, thank you very much. Maybe just to summarize, as very nicely addressed by Gizem, these are all rock sites. And the motion, you see, these are the recordings obtained at this Izmir Bay rock sites. This is the average response. And this is what we would predict by ground motion equations. So as you can see that definitely unusually long period energy is out there in Izmir Bay at our rock sites. So this is something that we don't expect. And remember, that is the period range of most of our buildings that collapsed there. I'm just talking about rock sites yet. So this is an unusual behavior as we don't anticipate this in a general sense. In a local sense, we're well aware of the situation in Izmir. We have done some deconvolution studies. Gizem, would you quickly address that? Please, time is limited. I want you quickly go over it.
We have done some deconvolution sites. Deconvolution means we basically did the backward site response analysis to see what is happening at the bedrock levels. When I say bedrock level, it is 1,500 meter depth, and for a VS value of 3,000 meter per second. We try to mimic.
Gizem, may I interrupt?
Yes,
Gizem, sometimes your connection, your quality of your connection is poor.
Sorry, hocam.
So let me finish this part. I'm sorry, but what we have done is basically we did the convolution studies at this rock sites, and we tried to find out what was happening at Izmir Bay at 1,500 meter depth. I'm talking 1.5 kilometer depth, because we would like to understand how the basin of Izmir was shaken at the rock level. And we have done it beautifully. When I say we, you know, or faculty members very well, actually it is our graduate students that did the work. We are the ones who are just guiding the work. We found the rock level within motions, and then these are the summaries of it. And guess what? Look how similar they are. So we said, okay, we have a good understanding about basically what was happening at the rock level. So having done that, we repeated the same exercise. Now for generic rock sites. Remember, we engineers, we love to produce generic rock sites, and we try to question if generic rock motions in Izmir will capture this response. As you see that these are predictions and these are the actual recordings. Generic rock profiles do not really capture the rock response in Izmir Bay, because in Izmir, rock profiles have the unusual, unique nature that because of the extreme faulting system in Izmir Bay, these rocks are very fractured. And then quite surprisingly, when you go deeper, shear wave velocity does not necessarily increase. You know, that produces a lot of basically refractions in the system. So if you neglect that event through basically generic rock profiles, then what you get is over modeling or over amplification of generic rock motions. One essence or one conclusion from this is generic motions do not really model a rock response in Izmir. Let's talk about soil sites now. Makbule, would you help us with describing what happened at soil sites in Izmir Bay?
Sure, hocam. In Izmir Bay, we have around 7 strong ground motion stations located on soil site. We also have a look at the Güzelbahçe and Urla stations as well to understand what is happening. So I will quickly focus on the response spectra in this plot due to time limitation. When we look at the response spec in comparison with the GMP, around some of the stations located in the south part, for example, this is Urla. The GMP's estimations are doing kind of okay. And if we go further, now we are located in Güzelbahçe. The shear wave velocity is around 460 meters per second. The GMPs are doing again okay. We are located in the south of Izmir Bay right now. Again, let's have a look at Buca Station, 468 meters per second. Oh, it's over predicting right now. And now we are very close to Izmir Bay. It's Çamdibi Station. VS30 value is relatively lower, 250 meters per second. And now we have the Bayraklı region. The GMPs are not very good predicting. The difference is about 4 to 5 times as we cross the basin and proceed to the north. The GMPs, yes, we are in Yamanlar the region right now. Again, the PGA, the GMPs are not doing okay.
Thank you, Makbule. Again, a comparison of soil sites in Izmir Bay, average of them, and comparison with ground motion prediction equations. In the average, ground motion prediction equations are not very off, but you saw that individually, if you look at the individual records, the scatter is significant, and especially side effects. When I say side effects, please don't forget that side effects include both soil amplification, basin effects, and topographical effects. When I say topography, it's not just surface topography, but it is also includes subsurface topography. So it is a general term that we use to define the phenomena. To cut the long story short, side effects really, as you can see, that significantly changes acceleration levels. If you talk about PGA level by a factor of 2 to 3, so 300% amplifications. When I basically normalize it, the recorded values with the predicted values, you can see that the answer can be off by a factor of 60%, as you see in this plot. Having done that, then next what we did is basically we tried to understand this rock sites, and we did the convolution. Makbule, would you quickly please tell us what happened?
Sure, hocam.
We deconvolved the soil sites.
Yes, we repeated the same exercise for the soil sites. We started with Buca, Güzelbahçe. We again constructed shear wave velocity profiles up to a depth of 1.5 kilometers when we reached the shear wave velocity of 3,000 meters per second. And we basically run an inverse propagation of the surface ground motions and find out the within rock motion for each 9 soil strong ground motion station.
Thank you so much, Makbule. These are the within motions at 1,500 meter depth, that means at the seismic bedrock level, obtained by deconvolution of the soil site. Again, their average value, and I'm sorry, this was the values that we obtained from rock motions, and these are from the soil sites. You see one anomaly. One site is really like, you know, falling out of the range that we expect. This is our 3518 Konak station.
Yes, hocam.
Yes, they are also saying Konak station. And so what is going on here? And then after investigating that, we found that there is an underground parking lot. So which is interfering with our recordings. So experts who are working at that station, please be careful. We exclude it from our database. And average of rock withins, obtained from soil sites. Look how similar they are. By the way, when I say similar, I'm talking in terms of uncertainties in earthquake engineering. Some of you may say, oh, they don't look similar, but to us, they are very similar. Having said that, okay, now what we understand here that in Izmir Bay, definitely we're capable of understanding the rock motions, bedrock motions, and also it is not really, it cannot be modeled by ground motion prediction equations. So to be able to understand what happens in Izmir Bay, we studied the background. When I say we, that was a big group of researchers that we collaborated together. Thanks to a lot of researchers that did this work earlier under the supervision of Professor Mustafa Akgün, who's also a team member. Borneo Plain is a unique plain. It is basically a pot surrounded by hills and mountains everywhere. The only exit is Izmir Bay. And the deep deposits there is up to 500, 600 meters. We have deep alluvial deposits there. Here is a profile that underlies that, and there are some creeks that are passing, that are forming the Bayraklı Basin. Typical soil profiles, time is limited, but please notice that we're talking of hundreds of meters of soil deposit at the site. And now what we did is we use rock motions, and we try to see if we can mimic what happened in Bayraklı region. We did site response analysis. This is the outcrop recorded motion. These are our rock outcrops. We did deconvolution. We applied at the base of the soil profile we developed for Bayraklı, and the blue lines or the curves are the response of Bayraklı estimated by us. Red and black are the recorded values. Look how beautifully they are matching. So that means, yes, we can mimic, we can analyze the response. The model we generated is quite satisfactory. Having done that, basically what we did is we used the transfer functions, how the amplification at the rock level was amplified. Look at it. They're amplified by a factor of 7 to 16, 17 when they're traveling from the within rock all the way to the surface, or when you compare it with the outcrop rock and with the outcropping soil motion. So this is huge amplifications. And that definitely suggests basin effects and side effects. And whichever aspect you look at it from elastic response spectra, you look at it from Fourier amplitude comparisons, you can look at it from H to V ratio comparisons, wherever you look at microtremor studies, they all suggest the same thing. Don't forget that this pink range recommends or shows the range of structures existing in Bayraklı. So to cut the long story short, we performed a lot of this analysis, specific now for Bayraklı, and guess what? Rock outcrop, rich with long period energy. It comes rich at the within motion level. And then soil site significantly amplifies that motion. And now we have a monster. When I say monster, relatively speaking, this record itself is not a monster, but amplifications are monsters. So remember, rich long period motion at the source, rich long period rock motions in Izmir, rich long period within motions at 1500 meter depth, amplified by soil, further amplified by 7 to 9 story buildings that significantly increase seismic demand from the structure. So structural damage is another issue. But what I'm talking about is increased seismic demand due to soil and rock site effects. Having said that, to understand the basin effects, we're working on 2D and 3D assessments, which is basically like on our way. We will work on it. I know I have used a lot of time. No, not really, actually. I am following my schedule really well. I have a couple more minutes, so maybe I can slow down. We haven't stopped here because everybody is asking the same question. Remember, this is not a Izmir design basis event. We're talking about an event that happens 65 to 75 kilometers away from Izmir Bay. Rock motion PJ levels in Izmir, 0.5, 0.7, 0.9 Gs. So we're not talking about, I'm sorry, did I say 0.9? 0.09, 0.05, 5% G, 8% G. We're not talking about really significant excitations. They are amplified to levels of 0.15 to 0.20 G by site effects. in Bayraklı. However, this is not the design basis event. So the question is, what will happen if we have a design basis event? So we simulated a deterministic scenario just to briefly answer that question. A magnitude 6.9 event on Izmir fault at rock sites. We expected to what happened at those rock sites. These are our predictions by using ground motion prediction equations. Don't forget that ground motion prediction equations are unconservatively biased for Izmir Bay. Real life in Izmir Bay or real rock sites in Izmir Bay, they love to amplify long periods. Well, usually, this is not something that we expect from those sites. And then we selected some earthquake records. By the way, this is a very informative event. This is probably, if we agree that the magnitude is 7, this will be the largest normal event in our relatively moderate to high intensity database. So the only record that we have or event is from Italy. That is a magnitude 6.9 normal event. So we don't have very much records from normal events at these magnitude levels. So we chose some rock motions. We fit it to our basic ground motion prediction equations, and then we did some site response analysis. Those are the records. By using the model that we use, Outcrow, we did the convolution for the scenario earthquake. And this is what we expect in Bayraklı after an event. Again, a deterministic scenario. Please understand the uncertainties. And also, we believe this is unconservatively biased. Remember, ground motion equations are a little bit exceeded at the rock site. So these are probably will be exceeded by a real event. As compared with the design basis, elastic response spectra. I'm not saying buildings will collapse, will be damaged. Remember, this is an elastic response spectrum. But basically, the essence of this exercise is to simply say that Izmir Bay is a special place. Both topographical, geological, geotechnical conditions, faulting systems, it is a special place like Mexico City. Deep lake deposits there that loves to amplify things. So this is not a phenomena that we don't know. This is a phenomena that we know it. And thanks to a lot of researchers who worked in Izmir, it has been written, discussed, presented, analyzed in the last 30 years by many authors. It is not like that we're just learning those things. We know those things. So, concluding remark, we need to do something for Izmir Bay. This is a unique, special place. Maybe our NIHERP amplifications, they don't work here. Eurocode don't work here. Turkish code, I believe, this is a unique place. So we need to do something special for this region where significant long period amplifications were expected. This is the team. And concluding slide, remember, we're talking about the technical details, but at the end of the day, we lost a lot of lives there. This little cutie, she was saved 65 hours after the event. Remember, probably most of you followed it. She stayed there all by herself under the rubbles. And after the event, you all remember that she was holding her savior's hand. This became the symbol of the earthquake. So, I guess I don't need to say much. Thank you, Gizem. Now you can take the host away from me.
Thank you, my dear colleague, Ms. Ilgaç, and my advisor, Professor Çetin. With our speeches now, session 5, site effects and geotechnical findings has been ended. Now we will move on to the session 6, which is about structural damage and findings. And the next speaker will be Dr. Bekir Özeray.
I hope you can hear my slide.
Yes hocam.
See my slide and see my slide. Okay. Thank you, Gizem. Now, dear participants, dear professors, I welcome you all. This part of the webinar devoted to the observations on evaluation of the damage on structures. In this context, I will start with introducing the characteristics of the building stock in Izmir. At this point, I would like to express that Gizem Nur Talas Soylu, a graduate student of mine, has taken the raw data and compiled it for Turkey and for Istanbul before for graduate studies. After the earthquake of Izmir, I have recompiled and reanalyzed it as raw data, particularly for Izmir. The data compiled and presented in this study is taken from the 2000 building census for pre-2000 buildings and the building occupancy permit statistics for post-2000 buildings. Both of these are disseminated by the Turkish Statistical Institute, the raw version of this. And I'd like to express that the 2000 building census gave the data in periods of 10 years, whereas the building occupancy permit statistics disseminate the data in a yearly basis. On this slide, you can see the previous building census studies in Turkey that have been made in 1965, 1970, and 1984. A 2000 building census includes all of this information, and you can also see the history of the earthquake codes in Turkey. Among these, the 1975 earthquake code was not a mediocre code, but it lacked in a forced building supervision system. So in 1998, earthquake code improved the contents as well as introduced a compulsory building supervision system, which has been taken under effect starting from the year of 2000. According to data we have, there are 670,000 buildings in Izmir by the end of 2018. 89% have residential or mostly residential buildings, whereas about 11% are non-residential buildings. And these buildings in Izmir contains about 1,710,000 dwellings. And you can see on the slide the distribution of buildings as well as the dwellings in a municipality base. And the building stock in Izmir can be classified basically into three construction types, which are reinforced concrete, either frame, wall structure, dual wall and frame interaction systems, as well as the masonry structures and others. And the statistics show that about 69% of the buildings in reinforced concrete, whereas 30% of it in masonry, only less than 1% of the whole building stock is either structural steel wood frame or some other structural systems. Considering the resolution of the Turkish the TSI data and the structural design regulation that was in effect on time, we can classify the buildings in terms of their construction year into three, as the pre-1980 buildings, which can be accepted as a low-code buildings, whereas the buildings that has been constructed between 1980 and 2000, which can be accepted as a mid-code buildings, and the post-2000 buildings, which can be accepted as high-code buildings. Similarly, the number of stories can be used as a classification parameter because previous earthquakes showed that this affects the vulnerability of structures a lot, especially the reinforced concrete buildings. Thus, we have classified the buildings as 1 to 3 story buildings as mid-rise, and buildings with 9-story or more are high-rise. And the distributions for these classes shows that the mid-rise buildings, which are 4 to 8 reinforced concrete mid-rise buildings, which are 4 to 8 story, so that has been constructed between 1980 and 2000. And this class corresponds to one of the most vulnerable groups in Turkish building stock, constitutes about 11% of the reinforced concrete buildings in Izmir. And that 11% corresponds actually more than 50,000 buildings. So there are more than 50,000 buildings in Izmir that can be accepted as relatively highly vulnerable compared to the other groups in this slide. This is another slide comparing the number of completed new buildings within approximately 10 years of intervals from 1930s to 2018. You can clearly see the rapid increase in the number of new buildings constructed of 60s. And note that more than have been constructed in the 20-year period, which is from 1980 to 2000. And actually, about 78% of the building stock have been constructed before 2000, so they can be assumed as without the confirmation to the modern design codes. This is the empty half of the glass. We can also focus on the other half of the glass. So actually, about 12% to 20, more than 20% of the building stock in Izmir is being expected to satisfy the earthquake-resistant design characteristics. Finally, the building stock in Izmir can also be investigated in terms of the variation of the average number of dwellings per building within a 10 years periods of intervals. That will give us information about the building height, the number of stories, because as the number of dwellings increases, usually there is a positive correlation between the number of dwellings in each building and as well as the number of story. So the statistics shows that the average the average dwelling number per building increases 100% within the last 40 years. And this increase is 50% within the last 9 years. So the number of story of buildings and as well as the number of dwellings is rapidly increasing in Izmir. There are some similarities between Izmir and other big cities of Turkey, but this is much more pronounced for Izmir, especially, for example, compared to Ankara, the capital of Turkey. So this indicates the frequent construction of high-rise buildings, as I said, and regarding the average number of stories, or let's say regarding the average number of dwellings in districts of Izmir, I can say that it is highest in Bayraklı, where we have seen lots of collapses. This is about 5.3, but rather than the absolute quantity, this is the highest one. And it's also high in Karabağlar, it's more than 5, and it is 1.3 as the lowest in Kınık. So further statistics and comparisons can also be made, but I think this frames the most important characteristics within the scope of today's webinar. So thank you very much for all your participation.
Thank you, Dr. Ay. Our next speaker will be Dr. Erdem Canbay.
Thank you. Yes. Okay. Today I want to share my observations on the reinforced concrete buildings. I want to also acknowledge other contributors, all contributed to this information that I'm going to share here. I'm going to talk especially for Bayraklı district because over there a lot reinforced concrete buildings suffered. They got significant damage. Despite the location, which is almost 60 kilometers away from the epicenter, we have 13 total collapse, 110 heavy damage, and many buildings with non-structural damage on infill walls. Over there, the spectral acceleration was approximately 0.35 g in the period range of 0.8 and 1.4 seconds. Surely it is above the service earthquake level, but it is just approximately 1/3 of the design level earthquake ground motion. And we have heavy damage or collapsed buildings, especially for in between 7 and 10-story buildings constructed before 2000. Here you see the red ones either collapsed or have heavy damage. I want to show you, give you some cases. For example, I want to begin with the Barış building complex. We have here, as you see on the right, 4 identical buildings, twins, 2 total collapsed, 1 heavily damaged, and the other one, the last one, has just minimal structural damage. Yes, it has also heavy infilled wall damage. First, I want to begin with the survived one. Significant amount of infill walls in the ground floor as compared to the other 3 one, because the other 3 has no infill walls in the ground floor. It has a lot infill walls. And also the survived one has had a different contractor. I want to conclude something like this. Under small to medium size earthquakes, infill walls may increase lateral load carrying capacity if it may stay intact and may help the building survive. Here, this is the pictures of the Barış building complex. This is before the earthquake. As you see, there's nothing. It is totally empty, no infill walls, and you see the results after the earthquake. I'm not saying that if you have something like this, you will surely have such a result. No, I'm not saying this, but this is the outcome, soft story and weak story. This is the last one, the survived one. As you see, even before earthquake, you see it has infill walls. And after the earthquake, you see walls are inside, especially heavy damage on the infill walls, but it survived. Nobody died inside this building. Similar observations made on Cumhuriyet building complex. As you see, one building suffered a lot. There was a story here and totally collapsed, the ground story, and the other one stays over there. For the Aegean building complex, I want to make different results that we didn't see maybe during other earthquakes. In this building complex, we have 2 similar buildings, identical. And in one building, you see heavy damage, and the 2 stories, the first 2 floors totally collapsed, as you see the difference in the height. And the other one, almost no damage, but from the street survey. Outside looking, it looks perfect. If you go, however, if you assess that buildings also from inside, you see also a lot heavy damage on members, on the heavy damage on the columns, shear failure, another column inside, and also because of corrosion, there's a great loss of area on the longitudinal bars. In between 25 and 65% area already gone because of corrosion. And it is important. Sometimes it is misleading just looking to outside with the street survey. You can't capture everything. It is an important outcome. I want to also give an example for a new building. It is, as you see on the right-hand side, a new one. There is a shear wall core. Actually, while I am taking this photograph picture, it was behind me, the core. And there's as you see, a very large opening in the center of the slab. And all offices are located around the opening. Here you see everywhere there are office buildings. And we saw very, very heavy infill wall, non-structural wall damage in this building. And it is a new building. Here the problem was the core wall, the shear wall, was unable to restrain the interstory drift for the rest of the structure because there's no diaphragm action over there. There's a lack of diaphragm action. Most probably the problem was improper modeling and inadequate design, because if you model on the computer with infinitely rigid diaphragm floor action, on the computer you see a perfect behavior against earthquakes, but in reality it is not the case. You need a proper load transfer mechanism to the shear wall. You have to transfer the earthquake load to the shear walls. We saw a lot permanent deformation, therefore those buildings already demolished because of the joints or because of at the end of the columns. As you see on the joints, maybe you can't see it very much, but there was a 10 centimeter almost permanent deformation. And because of the improper, inadequate capacity or design, detailing, you may have permanent deformations, and we can't get it back, and therefore we have to demolish such buildings. I want to show a few slides very fast. First of all, the overhangs. As you see, we saw a lot heavy overhangs, the cantilevers, and those caused a lot damage on the building. And also itself, the cantilever beams has almost all cantilever beams underneath the overhangs has shear failure or shear cracks. Those are just simple pictures that we took. On the beam, you see here the shear cracks, diagonal cracks, or here you see the beam column or the beam shear wall connection, inadequate reinforcement. Due to the inadequate reinforcement, flexural failure, flexural cracks. Also, in a lot of walls, or shear walls or columns, we saw shear crack. As you see, those diagonal cracks, they suffered a lot. In Bayraklı especially, we saw also a lot stairs failure. Therefore, it is almost collapsed. It is very dangerous. And also non-structural walls, especially underneath the overhangs, almost all of them have heavy damage. Yes. Since we have a lot of students here, I want to very fast summarize the mistakes always made and we observed also in this Izmir earthquake. First of all, wrong seismic system selection. It is important, generally, the system, the framing system, the walls are not correctly selected and designed. Especially in Elazığ we saw it, but in Izmir also it is the same, almost the same. Discontinuous frames are very much, and there's not a good framing system. Generally, an architectural system is planned, and according to this, on this architectural plan, they try to put the load-carrying framing system, which is not a good approach, actually. Architects and civil engineers should work together, especially at this stage. I already gave the example for large slab openings. If you have very, very large openings on the floor, you have to consider it in your modeling. It is very important. Some or many buildings has no shear walls, which means that they never thought about the seismicity, earthquake during the design of such buildings, which cause inadequate lateral stiffness on the buildings. We saw some short columns. Surely we saw like the Barış building complex, soft and weak story, which can be vital. With just a few infill walls at the ground level, which retard or even prevent soft and weak story creation, can survive life and also can survive the building. The heavy overhangs, everywhere in Turkey we see it, is a big problem for Turkey. We saw also some pounding effects. Nearby buildings cause pounding during earthquake because of different seismic demands. And because of pounding, we saw some failures or damage. Surely the buildings that built before 2000 have also low concrete quality problem, but not just those before 2000 have problem. Also, even today, the new buildings have low quality concrete quality problem, because the target quality increased in time with years, I mean, and even today they can't shoot the target concrete quality. Even today we have problem with concrete quality. The construction incompatibilities with shop drawings, generally what we have at hand as drawing, as project, is not constructed at the site. It is a big problem. Bad workmanship, inadequate workmanship is another problem. Plain reinforcement fall for old buildings, the buildings constructed before 2000. We saw almost in every structure this problem, 90-degree hooks at the end of ties. As you remember, the end of the ties should be hooked 135 degree. They just leave it 90 degree, and they easily open up during the earthquakes. During the regular life without earthquake, they carry the shear force, no problem. But during the earthquake, they don't give the required confinement effect to the members. I have never seen any cross ties in shear walls or in the columns. There's no cross ties, no closely spaced ties at the member ends. As you remember, at the end of the columns, at the bottom and top end, and at the left and at the right hand side of the beams, there should be closely spaced ties, but we didn't see such closely spaced ties. The beam column overlooked. They never put any ties inside the joints. Even the problem for shear walls is the end zone detailing, because as you remember, the end of the shear wall should be column, and they skip this also. Those are the general mistakes we saw also in Izmir earthquake. If I should summary also the different outcomes already very well presented in the former presentation, there's a soil amplification and a basin effect in Bayraklı. Therefore, it should be considered. And maybe we should use a site-specific response spectrum for such places. First, you have to find such places, and you shouldn't just follow the regular code, and we have to use site-specific response spectrum. The infill wall damage, the non-structural separation wall, I mean, those walls are, first of all, significant because you lose a lot property. You have to repair them, and it is money. And more than this, they have those cracks, heavy crack on the infill walls, separation walls, have an essential role in the earthquake aftermath psychology of the people. Nobody wants to go back in their buildings. They have just infill wall damage and no structural damage. Maybe they can live, they don't need to go out, but nobody wants to go back in their apartment flat. Street survey is important, but sometimes misleading. You should be careful while you make a street survey. Sometimes you don't see any damage from the street walk around, but if you examine the inside, you may see heavy damage. You should be careful. It was very interesting in Izmir, we saw such cases. As I said, in the Barış building complex, the infill walls may be beneficial, contributing to the vertical and lateral load carrying capacity of the building, which will reduce the drift demand and prevent the collapse of building under small up to maybe medium-sized earthquakes. I already mentioned about the large openings. Be careful with the large openings in the slabs. You should be careful with the lack of regular structural system and continuous frame systems, because if you don't have a regular framing system, you can't transfer your earthquake loads to the earth and you will get damage. Corrosion is another big problem for Izmir. We saw in almost every building problem. Overhangs, I already mentioned about this. The last thing I want to mention is this. Here, the damage observed are due to the inadequacies and deficiencies present in the buildings, because the ground motion already mentioned was less than the design level. Although it was amplified, it was much less than the design level. And if you see a non-damaged building, it doesn't mean that it is seismically strong. No, it is a wrong impression for seismic competence. Okay, if you see a non-damaged building, it doesn't mean that it is its capacity is good enough or adequate for a real design level earthquake. Thank you, Gizem. That's it.
Thank you, Dr. Canbay, for your very informative speech. Now, our next speaker is...
Change the altitude. So now it's time for the response of the tallest building in Izmir during the earthquake. Well, our new code requires real-time monitoring of the structural response of the buildings of earthquake design class 1 and 2 that are taller than 105 meters. And the health monitoring systems on these tall buildings have to comply with the guidelines provided by the Disaster and Emergency Management Presidency of Turkey. And these guidelines are actually have been recently developed with two concurrent research projects that were undertaken at METU and Boğaziçi University. And within the scope of these two projects, a tall building in Izmir and Istanbul, respectively, were permanently instrumented. Okay, so today I will talk about the Mistral Izmir office tower. I will present its response to this magnitude 6 Izmir earthquake, its system ID before and after the earthquake, and I will wrap up with its performance level following the earthquake. Well, Mistral Izmir office tower is 216 meters tall. It has 48 floors with 2 basement floors. It's a composite building with buckling restraint braces. It was opened in December 2017, and its health monitoring system is active as of January last year. So here's the location of the building on the map. Here's a close-up view. It is in Konak district of Izmir, very close to the collapsed buildings in the Bayraktar region. And for those of you who know Izmir, this is the view from the top to the west. Well, the building has a trapezoidal footprint. It has 53 meter and 39 meter parallel sides in the north-south direction and 41 meter perpendicular side in the east-west direction. It has a square, the tower portion has a square footprint with 27 meter sides. The typical floor-to-floor height is 4 meters. It has 4 mechanical floors, starting from floor number 9, and at every 10 floors you have another one. While the structural system of the tower is consisting of reinforced concrete shear walls, U-shaped ones, 2 of them, and they are linked with steel coupling beams. It has reinforced concrete moment-resisting perimeter frames with circular composite columns and buckling restraint braces at floors number 19 and 39. While the BRB outrigger systems connect the corner columns to the core at 4 corners at these 2 floor levels. The foundation is 3.7 meter thick mat foundation on barrett piles. The soil group is D and the local site class is Z4 according to our previous code. The health monitoring system on the building is 4 uniaxial accelerometers and the triaxial accelerometer. And there are 7 alpha strong motion stations in the vicinity of the building. Well, here is the instrumentation scheme. Accelerometers were placed on 7 different floors. The typical instrumentation on a floor consists of 2 parallel uniaxial accelerometers in the north-south direction and 1 in the east-west direction. And in addition, at the base and at the top, you have 3 vertical accelerometers at 3 corners of the building. Well, here you see the floor accelerations before the earthquake. From left to right, you see the east-west translational, north-south translational, and torsional responses. And from bottom to top, you see the responses from the basement to ground, floor number 10, 20, 30, 40, and 48. And here are the Fourier amplitude spectra of these responses. And from the peaks, natural vibration frequencies were determined. Well, as structural engineers, we are more comfortable using periods, therefore let's switch to periods. So the fundamental frequency along both axes are 4.1 seconds, and the second mode periods are around 1 second. Well, now the response to the earthquake. Well, the epicenter of the earthquake is 71 kilometers away from the building. Here you see the floor accelerations. The maximum acceleration is 0.28 g at floor number 48. And at the basement, we have the maximum acceleration 0.11 g. And here are the floor displacements. The maximum displacement is 16 centimeters at the top. And here you see the short time Fourier transforms, and they basically show that higher modes were excited during the earthquake, especially the second modes. And here you see the comparison of the building-based motion with a number of code spectra. Here we have the our current code, the code for railways, highways, harbors, and airports, and our previous code. The red ones here are maximum considered earthquakes. The blue ones here are design earthquakes. The green ones here are frequent earthquakes. And the black one is the service level earthquake according to our new code. So the Izmir earthquake is definitely not the design earthquake for this building. At most, it can be considered as a service level or a frequent earthquake, because if you just take a look at to the period range here, we actually have very much less, spectral acceleration at above the service level or above the frequent level earthquake. All right, so here you see the comparisons of east-west translational natural vibration frequencies before and after the earthquake. So note that the frequencies are normalized with respect to their initial values, and the change in the fundamental frequency here is about 5%, and all others are less than 10% after the earthquake. And here you see the comparisons for the north-south translational frequencies. Once again, the fundamental frequency change is about 2%. All others are actually all less than 5%. And here you see the comparisons for the torsional frequencies, and the change is less than 10%. And here you see the before and after mode shapes for the east-west, vibrations. So note that the mode shapes are not changing at all. And here you see the north-south ones, no change once again, and the torsional ones, no change again. And here you see the finite element structural model of the building where uncracked gross section properties were used. And the match with the system ID results is actually unbelievably good here. So you see that all these numbers are right on, target. So this is the east-west, and here you see the north-south one here, okay, and the torsional ones, okay. All right, so now here, if you end up using the crack section properties according to our new code for frequent service level earthquake, you get these frequencies, okay, and they are about 10% less. Okay, and therefore now if we think about the change in the natural frequencies, remember in the fundamental frequency it was 5% in the east-west direction, whereas it was 2% in the north-south direction. Okay, so they are all below the predicted values from the our new code. Okay, and there is no change in mode shapes. The average drift is less than 0.1%. No structural damage, hence the building is in continued use after the earthquake. Okay. All right. So I'd like to acknowledge, these institutions and people. So AFAD for funding this project, Mistral Izmir Management for providing us with the opportunity to have the health monitoring system on the building. Ozan Çağlar İnanç for coordinating all these efforts. Süleyman Tunç for helping us in the health monitoring installation, and also Gümeş as the project assistant for this research. So I leave the screen to Dr. Caner, and we'll have the questions after the talk. Thank you.
Thank you, Dr. Çelik. Now our next presenter will be Dr. Alp Caner.
Oh, thank you. Yes, I think I'm sharing my screen and I am the last speaker. And Well, today, thanks for all this nice talk and presentations. And it was also really educative for me too, at the meantime. So I'm just going to talk about the seismic performance of bridges in the region of the city. And it is I looked at a certain line, and this certain line has about 19 bridges. Some of them are very close to the Bayraklı region and the Mistral Tower. And when Ozan Hoca showed a picture from Mistral Tower, I can see the two bridges that we investigated. So for those 19 bridges, there is no seismic induced damage. Basically, no movements, no exceedance of bending or shear, no cracks, no settlement, no loss of function in non-structural elements. Even the expansion joints didn't move. Like they put some asphalt, and I didn't see much. And there are twin bridges. They didn't pound to each other, basically. And I know all these presentations, most of us are concentrated to this region, and there are many bridges there. Like one of them is curved, one of them is the Mistral is on the right top corner, and one of the bridges is curved, and the other one is coming straight. And they have the speeds of 0.8 seconds and 1.5 seconds. And when I listen to all these presentations, it is close to the station, one of them, and it is this problematic area of the periods for earthquake engineers. The periods are between 0.8 and 1.5 seconds, but not much happened to these bridges. And I just want to show a video. Somebody from Facebook had the video. Like this just shows the earthquake moment. Basically, they shake. And when I watched this, I just remember from the past that we did a research in METU. So I just remembered one newsman, and he came to our lab and did have a ride. And so it can happen. You can be on the bridge while shaking, but what happens is the cars take more than the bridge, and at some point these cars also act like a mass damper, and they may reduce the seismic demands, and also there's this girder that fall down. What happened is there's an abandoned bridge construction, and they left the girders like this. This picture is taken 10 years ago, and I think it's not a good idea to leave a construction like that, and people were parking underneath these structures. So if you leave a girder alone with no lateral stability, with a little shake, they can just fall down. So this bridge was not under service. I just want to be clear on that. It's an abandoned bridge, abandoned construction with no stability for provided with at the moment. And the basic problem for those bridges is the alkali-silica reaction. It is developed in 20 years or 30 years of time, and they have many of this map cracking, and we are always also investigating this case. And this is the twin bridge where you saw the video with all this shaking. And when we looked at this joint, we didn't see much, anything like that. Just I saw while walking on that region, I just saw one piece of concrete, but it is just like 1 centimeter by 1 centimeter fall down from this joint, but I didn't see any real pounding problem, basically. And to tell the conclusion, as a conclusion, I can say that no seismic damage induced has been observed, and the problem is the alkali-silica reaction for this bridges. And from what I understand is at the vibration modes, probably this bridges has been subject to something like 0.3 G, but I know that by some cross-sectional checks, the bridges has more capacity than this one. And also we have observed similar responses in the last 3 major earthquakes in Turkey And the flexible supports at superstructure and substructure level is believed to help the successful seismic performance. And so it is kind of an isolation system. And also the bridge construction is strictly supervised by the government agencies. And I would like to thank to giving this opportunity to METU Earthquake Engine Research Center. And I think that's all I'll talk. Thank you. And I'll stop sharing.
Hocam, thank you very much for your speech. With Dr. Caner's
Thank you very
speech.
much.
Hocam buyurun.
Okay, Gizem, I think I can take over now. We hope that you have now a much better insight about the characteristics and effects of this earthquake in Izmir area. Now, we would like to move to question and answer session. If anybody has any question, they can ask, but please indicate to which part you are asking your question about. So anybody from the audience would like to have any comment or any questions regarding any part of our presentation?
Hello, can you hear me?
Yes, we can hear you. Hello?
Hello, can you hear me?
We can hear you. I cannot see you, but I can hear you.
Please identify yourself before your question.
Okay.
If there's a problem with your voice, you can also type your question through chat.
John and Makbule, it was a very nice presentation from all the research teams. Appreciate they gave us regarding the research to show those images and damages from the shear wall buildings. So are these part of the building frame system in which the shear wall is carrying the 100% load and the frame is designed for the gravity loads only, or is the dual structure system where the wall is taking a portion of a load, which is typically taken as 25%, and the frame is taking 25%? So that one clarification is required. And the second thing is that what are the aftermath of these damages, just to know if these damages are repairable, because such kind of systems are now popular. They're getting popular in our own region also. The structure also here in Peshawar are getting taller. Up to 30 stories are allowed now in where shear wall is here. So I just want to understand that if this system behave very well, earthquake. So what about the future? Can they be repaired? Thank you.
Okay, Professor Jambai, have you heard the whole question, or do you want me
not
to?
the whole, but okay. I believe that he's asking the new building with a lot of damage.
Let me.
He's asking, yes, yes,
Professor
please.
Jambai, let me rephrase what I have understood. He's asking about the percentage of shear walls in those buildings that suffer damage, whether the shear wall is a dominant structural system. For example, does it carry more than 75% or 100% of the base shear, or does it carry only about 25%? That was his first question.
Yes.
And his second question was the amount of damage that we have observed, is it repairable? Or what is the plan for such buildings suffering, heavy damage or moderate damage?
Okay, most probably, because we don't have the plans yet of that building, but most probably it was a dual system. Okay, most probably the shear that carries the earthquake shear percentage was like 75%. I don't believe damage was repairable, because we didn't see structural damage, and the non-structural damage was repairable. They can demolish the non-structural separation walls and build again, but they have to do something to that structure, because it showed that its behavior under earthquake is not acceptable. We have to strengthen or stiffen, let's say, the framing part also. Somehow they have to allow load transfer from the framing system, load transfer to the shear walls. But right now, we don't work much on this building right now. Okay, it was just observation.
Professor Canvar, he's also asking about the buildings with significant damage and heavy damage and collapsed. What about such buildings? What is going to be done about these buildings? Are they going to repair those damages? I think he also asked about the other buildings.
Oh,
like Barış Sitesi.
Heavy damage buildings already demolished.
Demolished, yes.
Yes.
And
yes.
and moderate ones?
They should do something, yes. They have to repair their buildings.
Okay, thank you, Professor Canvar. I hope that this fulfills your question and answers what you had in mind. Does anybody has any other question?
Ahmet Hocam, there's something on the chat, I think.
I'm checking. Yes. Ismail Karataş, I think he's asking a question, a general question. And he says, has there been any damage reported for other non-building or bridge structures, such as underground structures or wind turbines? Alp Hocam, there's no damage about the bridges, I guess.
Ahmet Hocam, no reported damage for underground structures.
Okay. And no reported damage for bridges as well, right?
Yes, except the one that is abandoned for construction, during construction.
Okay, that one is a special one. It was under
Yes.
construction, was incomplete. Yeah, the answer is that for wind turbines, there's no damage. They were all checked. Nejan Hocam is answering. And for other structures, except one bridge which was incomplete and it was in the stage of construction, that was damaged. Okay, there's no reported damage for infrastructure as far as we know. Okay. Any other questions? We still have some time.
Ahmet Hocam, as we wait, I have something in mind. It's not a question, but I just wanted to elaborate on Ozan Hoca's presentation. He has shown that the frequencies have changed. And we all know that the frequencies are dependent mostly on the mass and the stiffness. So after the earthquake, the change in the frequencies were in the range of 5 to 9%. And from visual inspection, there was no damage. So what might be the reason of this frequency reduction? And it was, I think, in the south east-west direction more than northwest direction, and but the fault was moving towards north. So I was expecting the main hit to the structure to be in the direction of north-south, but the frequency changes were in the east-west. So if Ozan Hoca can elaborate a little bit on this, I would be very happy.
Yes.
Yeah, sure. Can I share my screen?
Yes, hocam. Just for a second.
Depends. Gizem has to give you permission.
Buyurun hocam.
All right. So actually, the second question, the east-west motion is actually higher than the north-south motion here. So we have more reduction in the east-west frequencies than the north-south ones. And here, when we came up with the finite element model here, we used the uncracked gross section properties, and the match was actually perfect. Okay, so normally you may wanna use some crack stiffnesses there because your slab can easily crack under gravity loads, and you can have some cracks. But this is actually the most intense motion that this building has seen over its opening. From 2017. So what this actually suggests is that actually in our new code, there is crack properties for service level earthquake evaluation. And there you just have a minimum, reduction in the section properties. And if we actually use them in our model, we get about 10% decrease in the frequencies, okay? And therefore the frequency decrease here is actually less than 10%, and that actually makes sense. So here, what's happening is actually we might have some cracks in, slabs, columns, but they are just, minor cracking as we all expect. So it's not a major one.
Okay, thank you very much.
Thank you. Do we have any question? Yes, there's, I think, another one from Taner Wambui Muturi. He's asking that how was the reconnaissance path for the study determined? What parameters are taken into consideration? I think Önder Hocam and Erdem Hocam, you could probably answer if you wish. They ask about the path for reconnaissance study.
To be honest, I think the best resources at the beginning is to basically collect all the information from social media. So we have done that. Plus, we use some susceptibility maps, as we presented in our discussion about, for example, liquefied sites. Then we talked to our local colleagues. We asked their opinion about the path. And last but not least, we had a lot of groups, so we were broken into different subgroups, and all of us followed different paths. And on the way, thanks to technology, we communicated really well, giving suggestions to each other. This is what we have done.
Okay.
We collaborate with the ministry a lot and get very fast the real information from them. And they have modified their map every day, the damage map, and they collaborate with us and share their maps with us, and it was helpful, and we follow their directions, what they said, and go to this region like this. We got information from the ministry.
Okay, thank you. Okay, there's another question. It's a long one from İzzetcan Gümbey. His question is to Professor Özacar. Are you with us?
Yes.
Arda Hocam?
I think
okay.
the question is
Can you read the chat?
I mean, from the chat, according to the question, is too long, but question is about the moment magnitude calculation. Basically, at this point, we are not doing a separate calculation. There is more reliable estimates based on the waveform modeling, and those are around at least 6.9 to 7. The initial magnitude mainly comes from local magnitude and correlation with local magnitude to moment magnitude. So always initial magnitudes have larger uncertainty. So if the question goes to the fact that what is the magnitude of this earthquake, it's not less than magnitude 6.9 in that respect. And there is another question, if it's directed to me, I'm not sure, but
No, it's directed to Professor Çetin.
Previous one on return period. There's I think Alp is asking return period. Is it asking
yes.
about the return period of the earthquake?
Arda Hocam, it's from Aegean
Yes.
earthquake.
Is it the earthquake you are asking?
Yeah.
Yes.
The thing is, for return periods, you should be looking at each active fault and their slip amounts that they are having. So in that respect, it's hard to say there are many earthquakes generating faults in this region.
Okay, thank you, Arda Hocam. Önder Hocam, can you take the next one on the chat?
Thank you, Professor Yakut. Maybe a small note to Professor Caner's question. From intensity point of view, this event looks like it has a return period of about 50 to 72 year characteristic event. So this is not a big event. Regarding basically İzzet Can's question, thank you, İzzet. Thanks for following. We discussed that, but I will quickly share one slide. Gizem, I need the authority to share, please. So as a response, bottom line, maybe it's a repetition, but the rock response is unusual. So we have long periods, high energy in the rock motions. And again, okay, now I have the authority. I will quickly share that slide. Okay, this is the one that I'm referring. So from this event, you see that the rock outcrop has a lot of, this is unusual, and it is unique to İzmir Bay. And there are like some geological and geotechnical background for that long period rich motion. Again, when you basically do some deconvolution, you still have those long periods at the within motion. And then because of the unique nature of Bayraklı region, those long periods are further amplified, producing an increased demand for the 6 to 10-story buildings basically constructed in Bayraklı region. This is the essence of the conditions in Bayraklı and specifically İzmir Bay. Again, as was pointed out by a lot of our presenters, that is a special region. İzmir Bay is a special region, and I don't think we can perfectly solve the design problems by a country-wide valid code, but we should have something specific for İzmir Bay. I know that we have something special for high-rise buildings of İzmir region, but what I'm referring to is typical residential buildings, 7 to 9 story heights that I'm talking about. Thank you.
Okay, do we have any other question? We have a few more minutes.
Professor Yakut,
Professor,
just reminding, So just
Yes, please.
reminding about our Turkish presentations next week.
Yes,
You would like
yes.
to? Okay, thank you.
I will do that. Okay, for those of you who are interested, we will have the same presentations in Turkish next week, and we will have announcements. Electronic sources, okay. All right, if there is no other question, I think I'm going to close the webinar. I once again would like to thank all our speakers on behalf of ERC. And it was successful from our side, and we hope that you feel the same way. And we thank all the participants to come and join this webinar. So thank you very much once again.
Ahmet Hocam, if I made one more thing, if I
Sure.
may add one more thing. Since we are already thanking, I would like to thank our Rector Berşan Kök and our Dean Tuna Balkan for their immediate help for
Yes.
reaching to the site, for the permissions and partial support. So I would like to thank every speaker too, and the guests for the nice questions.
Thank you. Evet arkadaşlar. Hala gitmek istemeyenler var.
Kusura bakmayın. Thank you to everyone.
Efendim hoşça kalın. Görüşmek üzere.
Hoşçakalın.
Tekrar görüşürüz.
Ismarladık.
Herkese iyi hafta sonları.
Görüşmek üzere.